Start with you, not with your relationship, not with your job, not with your money, but with you. Good morning to one and all present here. On behalf of PG and Research Department of Mathematics, DG Vaishnav College, I welcome all the PG students and CSIR aspirants. Pray, then let it go. Don't try and manipulate or force the outcome. Just trust God to open the right doors at the right time. Now, Tamutar Vatu followed by college prayer.
நீராறும் கடலொடுத்த நிலமடந்து எழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிழே எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्राणामे दृष्टिस्तरुणा नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनाम जगत्क्रीडति यो यतः ओम शांति शांति शांति.
This is C4 workshop, Chase, Crack, Conquer, CSIR net, which will make the CSIR aspirants to go to the next level. Today our research person, Dr. S.P. Vijayalakshmi, Assistant Professor, PG and Research Department of Mathematics, DG Vaishnav College, Chennai. Now I hand over the session to you.
Thank you, sir. Shall I start now?
Yes, ma'am. Yes, ma'am.
Thank you, sir. Very good morning to everyone. Today in C4 session, we will see the complex analysis. In the last class, that is yesterday, we have studied some basic concepts and the problems related to complex analysis. So today we will continue with Cauchy's integral formula, Cauchy's theorem, Morira's theorem, Liouville's theorem, and then maximum modulus principle, Cauchy's theorem. So we will see some problems based on this. So before going to the problem, we will see the definitions and the theorems based on this, and then we will see the problems. So first, we should know what is a simply connected region. So a connected region or a domain is said to be simply connected if a closed curve C contained in D has its interior contained in D. that is a region without any hole. So that is nothing but the simply connected region or a simply connected domain. So simple closed curve. So the simple closed curve is nothing but the Jordan curve. That is the end point should be same. That is z of h equal to z of k. If z of t is any curve and t lies between h and k, h less than t less than k, and if z of h equal to z of k for any two different points t1 and t2, then we say that it is a Jordan curve. So Cauchy's theorem, if D is a simply connected region and f of z is analytic in D and f dash of z is continuous in D, then integral over C f of z dz will be equal to 0. So D should be a simply connected region and f of z should be analytic in D and f dash of z is continuous in D. That is, the derivative should be continuous in D. Then integral over C f of z dz will be equal to 0. So where C is nothing but any closed contour contained in D. If f of z is analytic in a simply connected domain and C is any closed curve, so if C is any closed curve, then also you can say that integral over C f of z dz equal to 0. So this is a Cauchy's theorem. So the next one is the Morira's theorem, which is a converse of the Cauchy theorem. So if f of z is continuous in a simply connected domain, an integral over gamma f of z dz equal to 0, where gamma is nothing but any rectifiable closed Jordan curve, then you can say f of z is analytic in D. So f of z is continuous in a simply connected domain, an integral over gamma f of z dz equal to 0, then you can say that f of z is analytic in D. So this is Morira's theorem, which is a converse of the Cauchy theorem. So the next one is Cauchy integral formula. Again, if C is a simply connected region and f of z is analytic in D, then for any A belongs to C, C is nothing but a simply closed rectifiable curve. So for any A belongs to C, f of A equal to 1 by 2 pi I integral over C f of z by z minus A into dz. So this is Cauchy's integral formula. So maximum modulus principle, that is using this principle we can say that the maximum value will be attained on the boundary. That is, f of z is analytic within and on a simply closed contour, then mod f of z reaches its maximum value on C. Okay, so the maximum value will be attained only on the boundary. So based on these ideas, we will see some problems related to that. So here f is a function from D to D, be holomorphic with f of 0 equal to 1 by 2 and f of half equal to 0, where D is a unit disk z such that mod z is less than or equal to 1. So we need to check which of the following is correct. So the first option, mod f dash of 0 is less than or equal to 3 by 4, mod f dash of 1 by 2 is less than or equal to 4 by 3, and mod f dash of 0 is less than or equal to 3 by 4, and f dash of half, that is a derivative, is less than or equal to 4 by 3, and the last option is f of z equal to z. So we need to check which of the following are correct. So here we are going to apply a Schwarz-Pick lemma. So actually based on that lemma, if f is a function from delta to delta be analytic, then we know that mod f dash of A is less than or equal to 1 minus mod f of A the whole squared divided by 1 minus mod A squared for all A belongs to delta. Okay, and then delta of f of A comma f of B is less than or equal to delta of A comma B. So this is a Schwarz-Pick lemma. So just we are going to apply this lemma. So here the question is actually here given with f of 0 equal to half and f of half equal to 0. So and D is a unit disk. So here delta is also a unit disk. Okay, in the lemma f is a function from delta to delta, so delta is a unit disk. So here, so applying this lemma, mod f dash of 0 will be less than or equal to 1 minus mod f of 0 the whole square divided by 1 minus mod A. So mod A is nothing but 0 here. So we'll be getting 1 minus 0. So for f of 0, we need to substitute the value. So given that f of 0 equal to half. So half the whole square, so which will be 1 by 4. So 1 minus 1 by 4 will be 3 by 4. So mod f dash of 0 is less than or equal to 3 by 4. And we will check mod f dash of half. So what is mod f dash of half? Similarly, applying the same theorem, you will be getting 1 minus mod f of half the whole square divided by 1 minus half square. So if you simplify, you will be getting 1 minus 0 because f of half is given to be 0. So 1 minus 0 divided by 1 minus half square, which is nothing but 1 by 4. So you will be getting 1 by 3 by 4 or 4 by 3. So we have to check whether the last option is true. So the last option is obviously false because it does not give the value f of 0 equal to half, because we are getting mod f dash of 0 is less than or equal to 3 by 4 and mod f dash of half is less than or equal to 4 by 3. So the options are, the first option is true and the second option is true, third option is also true because f dash of 0 is less than or equal to 3 by 4 and f dash of half less than or equal to 4 by 3. So A, B and C are true in this case. So D is obviously false. So you will see the next problem. Let A and B, C are non-collinear points in the complex plane and denote the closed rectangular region of the plane with vertices A, B, C. For Z belongs to delta, let H of Z equal to mod Z minus A into mod Z minus B into mod Z minus C. So the maximum value of the function. So the maximum value of the function, we need to check whether the following options are true. So here given A, B, C, B non-collinear points in the complex plane and denote the closed triangular region of the plane. So the closed triangular region of the plane with the vertices A, B and C. And H of Z is given to be mod Z minus A into mod Z minus B into mod Z minus C. So we need to check whether the maximum value of the function is not attained at any point of delta or is not attained at an interior point of delta or is attained at the center of delta or it is attained at the boundary point. So we need to check which of the options are right. So for this problem, we are going to apply the maximum modulus principle. So by the maximum modulus principle, we know that the maximum value will be attained on its boundary. Okay, that is if f of z is analytic in a bounded domain and on its boundary, then mod f attains its maximum on the boundary. Otherwise, f is a constant. So the maximum value will be attained only on the boundary. So based on that, here f of z equal to z minus a into z minus b into z minus c. So this is analytic on its boundary. So mod f of z is equal to h of z attains the maximum value only on the boundary. So the option D is right. It's attained at a boundary of delta. Because this is not true, it's not attained at any point of delta, not attained at the interior point of delta, it's attained at the center of delta and is attained at the boundary point. So by the maximum modulus principle, we know that the maximum value will be attained only on the boundary. So the option D is right. Okay, coming to the next one, let f be a non-constant holomorphic function in the unit disk such that f of 0 is given to be 1. Then it is necessary that there are infinitely many points z in the unit disk such that mod f of z equal to 1. So this is the first option. The second option is given to be f is bounded. The third one, there are at most finitely many points z in the unit disk such that mod f of z equal to 1. Last one, f is a rational function. So we need to check which of the four in this four options, which options are true. Okay, so given f is a non-constant. So f is a non-constant holomorphic function in the unit disk such that f of 0 is given to be 1. So we need to check which of the options are true in this case. So here by the open mapping theorem, f of d is open. So now what is your A? There are infinitely many points in the unit disk such that mod f of z equal to 1. So there are infinitely many points are there. So you can say that f of z is true. And the second option, f is bounded. So f of z equal to 1 by 1 minus z and f of 0 equal to 1. So in this case, f is analytic indeed, but it is not bounded. F is analytic, but it is not bounded. So the option B, f is bounded. So that is not true. And the last one, e power z is not a rational function. So e power z is a rational function. So that is false. E power z is not a rational function. Okay, so we can say that A is true. Okay. So the next one, consider I1 equal to integral over C dz by z minus a, which is equal to 2 pi I, and I2 equal to integral over C z minus a the whole power n dz equal to 0 for n not equal to minus 1. But C is a circle, mod z minus a equal to r. So we need to check which of the following are true. So given that I1 is true but I2 is false, the second one I1 is false but I2 is true, and the third one both I1 and I2 are true. So neither I1 nor I2 is true. So we need to check the following, whether I1 is true or I2 is true or both are true. So here we have the circle mod z minus a equal to r. So z minus a can be written as r e power I theta, or you can say dz equal to I r e power I theta into d theta. So here I1 is nothing but integral over C dz by z minus a. So by substituting and simplifying, we are getting that is equal to 2 pi I. So here f of z is nothing but z minus a the whole power n, where n is not equal to minus 1. So this is analytic everywhere within the circle mod z minus a equal to r. Therefore, by the Cauchy theorem, we know that integral over C f of z dz equal to 0. Therefore, substituting f of z, will be getting z minus a the whole power n into dz equal to 0 for n not equal to minus 1. So you can say that both I1 as well as I2 are true. So I1 is dz by z minus a. So we are getting I1 equal to 2 pi I, and I2 which is equal to integral over C z minus a the whole power n into dz equal to 0. So both I1 and I2 are true. So the option is C. Coming to the next one, the value of 1 by 2 pi I integral over mod z equal to 3 e power z divided by z minus 2 into dz. So we need to find the value. So by saying this, you can apply the Cauchy integral theorem. So by Cauchy integral theorem, we know that 1 by 2 pi I integral over C f of z by z minus a into dz equal to f of a. So that is Cauchy's integral formula. So here f of z is nothing but e power z. So this is of the form f of z divided by z minus a into dz. So here in place of a we have 2, and in place of f of z we have e power z. So by Cauchy integral theorem, so the value is nothing but f of a. So here a is 2. So we'll be getting f of 2. So what is f of 2? F of z is e power z. So f of 2 will be e power 2. So e power 2 means the option is C. So the value of the integral this is e power 2. So just we are applying the Cauchy integral theorem, that's all. So the next one, if f of z equal to z power 5 minus 3i z squared plus 2z plus I minus 1 and C encloses zeros of f of z, then integral over C f dash of z by f of z dz will be 0 or 5 pi I or 10 pi I or none of this. So we need to find the zeros. So for to find the zero, so this is of the form f of z by C encloses zeros of f of z, then integral over C f dash of z by f of z dz. So here we can apply the argument principle. So by the argument principle, we know that integral over C f of z d f dash of z by f of z dz is 2 pi I into n minus b. So n is nothing but the number of zeros, and P is nothing but the poles. So N is zeros and P is the poles of f of z. So for this problem, if you find the number of zeros and number of poles, then we can easily find the answer. So the given function is z power 5 minus 3i z squared plus 2z plus I minus 1. So here we need to find the number of zeros and number of poles. So here, if you see, there is no poles, because how will you find the poles? Equating the denominator to 0. So here we don't have any poles. We have only the numerator term, that is z power 5 minus 3i z squared plus 2z plus I equal I minus 1. So that is your f of z. So there are no poles. So P will be equal to 0. And N is nothing but the number of zeros. So zeros are given by f of z equal to 0, equating f of z to 0. So if we equate this to 0, you can say that the number of zeros of the function f of z is 5, because we have z power 5 minus 3i z squared plus 2z plus I minus 1. So the number of zeros, that is N is equal to 5 and P equal to 0. So substituting in the argument principle, we will be getting 2 pi I into N minus P. So N is 5 and P is 0. So 5 minus 0, which is 5. So we'll be getting 10 pi I. So 10 pi I, the option is C. So coming to the next one, consider P of z equal to z power 10 minus 6z power 7 plus 3z cube plus 1 and mod z less than 1. Then P of z is analytic on mod z equal to 1. P of z has 6 zeros inside mod z equal to 1. P of z has 7 zeros inside mod z equal to 1, and only B is true. Only B is true. Okay, that is P of z has 6 zeros inside mod z equal to 1. So we need to check which of the following are true. So actually here we need to find the number of zeros inside the disk. So to find the number of zeros inside the disk, we can apply the Cauchy's theorem. So by Cauchy's theorem, here the function P of z is given to be z power 10 minus 6 z power 7 plus 3 z cube plus 1. So here let us choose f of z equal to minus 6 z power 7 and g of z equal to z power 10, the remaining term, that is z power 10 plus 3 z cube plus 1. So here we have to choose the f of z as the highest coefficient. So if you see the coefficient, here the coefficient of z power 10 is 1, the coefficient of z power 7 is 6, and the coefficient of z cube is 3, and then we have the constant term. So since the coefficient of z power 7 is 6, we will choose f of z to be minus 6 z power 7 and the remaining term to be g of z. So now P of z can be written as f of z plus g of z. So here both f of z and g of z are analytic because they are polynomial function. So both f of z and g of z are analytic. So now we will find, we have to check whether mod g of z is less than mod f of z for Cauchy's theorem. So if g of z is less than f of z, then you can apply the Cauchy's theorem. So for that we will consider f g of z divided by f of z. So here g of z is z power 10 plus 3 z cube plus 1. So just substitute that z power 10 plus 3 z cube plus 1 divided by f of z is minus 6 z power 7. So by applying the triangle inequality, this is less than or equal to mod z power 10 plus 3 z cube and then plus 1. So this divided by 6 into mod z power 7. So if you simplify, we know that mod z is 1, mod z is less than 1. So if you apply, you will be getting 1 plus 3 plus 1 divided by 6, so which is less than 1. So by Cauchy's theorem, you can say that P of z and f of z has the same number of zeros inside C. So f of z is nothing but z power 7. So since f of z has 7 zeros inside C, we can say that P of z also have 7 zeros inside C. So this is Rouch's theorem. So Rouch's theorem, that is, we can write the function by using the Rouch's theorem. P of z can be written as f of z plus g of z. So f of z, you can choose the highest coefficient, that is z power 7 is 6. So you can choose f of z equal to minus 6 z power 7. Okay, the modulus of the coefficient. So here the coefficient is 1. Here the coefficient is mod minus 6, so which is 6. Here the coefficient is 3 and the constant term is 1. So let us choose f of z to be minus 6 z power 7 and g of z to be the remaining term. So and then we have to check whether mod g of z is less than mod f of z. So if mod g of z is less than mod f of z, then f of z and p of z will have the same number of zeros inside C. So that is Rouch's theorem. So since the condition is satisfied by Rouch's theorem, we can say that f of z and p of z has the same number of zeros inside C. So since f of z has 7 zeros inside C, we can say that p of z also has 7 zeros inside C. So the options are A and C. So the options are A and C. So P of z is analytic and P of z has 7 zeros inside mod z equal to 1. So these two options are true. So coming to the next one, here f of z equal to integral over C z squared minus z plus 1 divided by z minus 1 into dz, where C is a circle, mod z equal to 1. So we need to check which of the options are true. So the first one, f of z is analytic in and on C. In the second option, integral over C f of z equal to 2 pi I. The third one, f of z has simple poles. And the fourth one, f of z is not analytic in and on C. So we need to check which of the options are true. So in the, here given f of z is integral over C z squared minus z plus 1 divided by z minus 1 dz. So and z naught is given to be 1 because z naught divided by z minus z naught. So here z naught is nothing but 1. So here f of z is z squared minus z plus 1 and z naught is 1. So since f of z is analytic and z naught lies on C, we can apply the Cauchy integral formula. So here f of z is analytic because it's a polynomial function. So f of z is analytic and then z naught lies on C. So here z naught is 1. So z naught lies on C. Therefore, you can apply the Cauchy integral formula. So Cauchy integral formula, this should be A. F of A equal to 1 by 2 pi I integral over C f of z divided by z minus A dz. Or f of z naught equal to 1 by 2 pi I integral over C f of z divided by z minus z naught into dz. Okay, so this is a Cauchy integral formula. So based on this, if you apply, you can say that f of z here is nothing but z squared minus z plus 1 divided by z minus 1 is nothing but 2 pi I into f of z naught. So here z naught is 1, so you'll be getting 2 pi I into f of 1. Okay, so if you substitute 1 in f of z, f of 1 is nothing but 1 squared minus 1 plus 1. So the answer will be 1. So 1 into 2 pi I, which is equal to 2 pi I. So what are the option? F of z dz equal to 2 pi I, that is true, and f of z is analytic on C. So that is also true. So A and B are true. Since A is true, D is obviously false and C is also false. So only the correct options are A and B. Okay. Coming to the next one, given f of z equal to integral over C z squared minus z plus 1 divided by z minus 1 dz, where C is given to be a circle mod z equal to 1 by 4. So f of z is analytic everywhere within C. F of z is not analytic, f of 0 equal to 0 and f of z has not simple pole. So we need to check which of the options are true. F of z is analytic everywhere within C. f of z is not analytic, f of z equal to 0, and then f of z has not simple pole. So here z not equal to 1. So z not equal to 1, actually the circle is mod z equal to 1 by 4. Since the circle is, the radius is 1 by 4, z not equal to 1, the point z not equal to 1 lies outside the circle. So since the point lies outside the circle, you can say that z squared minus z plus 1 divided by z minus 1 is analytic everywhere within the C. So within the region, this function is analytic, right? Because it is not analytic at 1. So when you put z equal to 1, the function is not analytic. It says us to be analytic. But that 1 lies outside this region, because here the circle is mod z minus mod z is equal to 1 by 4. So the radius is 1 by 4. So the point 1 lies outside the disk. Since the point 1 lies outside the disk, you can say that this function is analytic everywhere within C. So within the curve C, this function is analytic. Therefore, by Cauchy's theorem, you can say that integral over C f of z dz equal to 0. That is Cauchy's fundamental theorem. So if the function is analytic within the curve C, then integral over C f of z dz will be 0. So here the function is analytic everywhere within the curve, because the function is not analytic at 1, but 1 lies outside this region, right? Therefore you can say that this function is analytic everywhere, so within the curve C. And therefore, by Cauchy's fundamental theorem, you can say that integral over C f of z dz will be equal to 0. So what are the options? That is, it should be integral over C f of z dz equal to 0. So that is true. And f of z is analytic everywhere within C. So that is also true. So A and C are true. A and C are true in this case. So coming to the 10th one. So here the function f, function from C to C. So defined by f of z equal to e power z plus e power minus z. So has finitely many zeros, no zeros, only real zeros, as infinitely many zeros. So we need to check which of the options are true. So here f of z equal to e power z plus e power minus z. So we need to check whether it has finitely zeros or no zeros, or only real zeros, or infinitely many zeros. So how to find the zeros of this function? Just we have to equate f of z equal to 0. So if you equate f of z equal to 0, you will be getting e power z plus e power minus z equal to 0. Or you can say e power z plus 1 by e power z equal to 0. So 1 by e power z, if you take the LCM, you will be getting e power 2z plus 1 equal to 0. Or you can say e power 2z equal to minus 1. So taking log, you can say that 2z equal to I into 2k plus 1 into pi. So therefore you can say that z equal to 2k plus 1 divided by 2 into pi I. So the answer is 2k plus 1 by 2 into pi I. So it has infinitely many zeros. So for k equal to infinitely many values, we have infinitely many zeros. So the option is D. So the D option is true. So for all these problems, we are applying the basic concepts, that is the Cauchy integral formula. So we should understand the basic concept and the basic theorem. So only this basic theorem we are applying in the problems. So everyone should know the Cauchy integral formula. So if D is a simply connected region, so simply connected means there should not be any hole. Okay, simply connected region, f of z is analytic. So the function should be analytic in D. Then for any point A belongs to C, you can say that f of A equal to 1 by 2 pi I integral over C f of z by z minus A into dz. So this is Cauchy integral formula. And the Morira's theorem. So Morira's theorem is nothing but the inverse of the Cauchy theorem. That is, if the function is continuous, in a simply connected domain and integral over gamma f of z dz equal to 0, then you can say that f of z is analytic in D. So that is a converse of the Cauchy theorem. So you all know the Cauchy's theorem. If D is a simply connected region and f of z is analytic in D, f dash of z is continuous, then you can say integral over C f of z dz equal to 0. And the Cauchy fundamental theorem is if the function is analytic that is on an interior of C, then you can say that integral over C f of z dz equal to 0. So that is Cauchy's fundamental theorem. So we should know the basic concepts of all these things. So in the next class, we will be seeing the problems under Taylor's theorem and then the Lorentz series and then contour integration, etc. So thank you. So I want everyone to go through the problems which we have discussed today and try to work out the problem in the note. And in the next class, we will discuss the problems based on the Lorentz series, Taylor series, and then the contour integration, etc. Thank you all.
Thank you, ma'am. Thank you,
Thank
ma'am.
you, sir. Thank you, sir.
We wish to express our gratitude to our resource person for being with us event. Your presence and explanation are very useful for our listeners. I would like to thank Professor R. Venkatramanan at PG and Research Department of Mathematics for organizing this C4 workshop. I am very proud to inform about our next webinar titled Navellina Theory and its Application. Resource person Dr. S. Rajeshwari, Assistant Professor, Department of Mathematics, Presidency University, Bangalore, will be held on 27th February at 10:30 a.m. Our next C4 session will be held on 27th February at 6 p.m. Thank you.